24 hours in a day, and I get to do math, hey hooray. Y equals mx plus b with Mr. Ng, we're making history. Pythagoras, Euclid, and Gauss learn the math and you'll become the boss.
Hey guys, let's go over lesson 3.3, simple random sample. What's our learning targets? Learning target number 1, describe how to obtain a simple random sample using slips of paper or technology. Learning target number 2, explain the concept of sampling variability and the effect of increasing a sample size. And learning target number 3, use simulation to test a claim about a population proportion. All right, let's go into learning target number 1. How do you describe how to obtain a simple random sample using slips of paper or technology? A simple random sample, and the letters of that are SRS, that's what the abbreviation is, of a size, and the size we're going to use letter N. Consists of N, or unknown amount of individuals from a population, chosen in such a way that every set of N individuals has an equal chance to be in the sample actually selected. We can also use technology to choose an SRS. This is especially helpful when the population is large. We can use an acronym to help us called DARE. So, what is our first letter of DARE? The first one we're going to use for DARE is digital. Digits, not digital, digits, numbers. Give each individual in the population a distinct numerical number from 1 to however many you have in there, where n is the number of individuals in the population. A good question you're going to have to answer is, which numbers are needed? All right, let's do our next one for DARE. This would be assign. What are the digits equivalent to? And then the next one, for R's, there's actually 2 of them. What do you do about repeats? And how do you randomize? For repeats, the question is going to be, are repeats allowed? Are any numbers skipped? Good question to ask. When choosing an SRS, we make the selections here without replacement, or you have to kind of tell us if you're going to replace the numbers or not. That is, once an individual is selected for a sample, that individual cannot be selected again. Random sample generators sample numbers with replacement. Meaning you'll see repeated numbers. So it's important that you explain that repeated numbers should be ignored when using technology to select an SRS. That was repeats. Let's go ahead and talk about how to randomize. Use a random number generator to obtain n number integers from 1 to whatever it is. So you say, I'm going to select 100 students out of Savannah High School to give them a college scholarship. So that will be the numbers 1 to 100. Using a calculator, you'll press the buttons math and then select probability. And under the probability window, you'll click random int. And then to complete the command, you're going to do random integer and then 1 comma, however many numbers you want. So if you want 100 people, you would do something like this. You can also write everyone's name on a piece of paper and draw from a hat. Just draw a hat, or write hat there. And then we're also going to use a random digit table. So how do we randomize again? We use dare, digits, assign, repeats, randomize, and the last part is E. When will it end? When will you stop taking digits? So that was page 1. Let's move on to page 2 with some examples. All right, page 2, let's do an example. Example number 1, how safe are these trucks? A safety engineer at an automobile assembly plant knows that 180 pickup trucks will be assembled tomorrow. To meet the federal regulations, the engineer must select 5 of those vehicles for safety testing. So we're going to use a piece of paper, slips of paper, and a number generator. So I'm going to go ahead and use my acronym. DARE. And if I use slips of paper, what numbers am I using? Whoops, too thick. Use numbers 1 to 180. Those are the digits that I'm using. Same thing, I'm going to use numbers 1 to 180. How do I assign them? Basically, each truck gets one number, right? Truck 1 goes to number 1. Truck 2 gets number 2. And we can just, same thing. That's how I'm going to assign these. So that's how I'm assigning the numbers. Okay. What do we do with repeats, and how do we randomize? Well, I'm going to ignore repeats. Ignore repeats, because I don't want to pick the same truck twice. Ignore repeats, because I want 5 separate cars. Okay, so for the slips of paper, then I'm gonna use same size paper. Use same size paper. Same size paper. Place in a hat. Place in a hat. Mix well. And pick. Okay. Let me just finish that one up. So how do I end this? After 5 trucks selected, comma, stop. Okay, ones of you use technology to randomize. Well, in the technology, I need to generate 5 random, that says random, integers. And I guess that one actually makes more sense to ignore repeats, because it does, we talked about repeats. Over here, you're not going to write a different truck twice, so cross that off. And when you have five unique numbers. Okay? Let's do a different example. Example number 2, hotel name. So this is now using a this is called a random digit table. The school newspaper is planning an article on family-friendly places to stay over spring break at a nearby Mathalicious beach town. The editors intend to call for 4 randomly chosen hotels. I'm going to stop right there. I'm going to underline that. They want an SRS of 4, where n equals 4, and to ask about their amenities for families with children. They have an alphabetized list of all 28 hotels in the town. Alphabetizing just helps with the organization. It's kind of the same thing as if you had a class roster of students. You'd probably do alphabetical last name. Use table D at line 130 to choose an SRS of 4 hotels. Okay, so if you actually click on table D, I will not do that in this video, but if you do, and you go down to line 130, you're going to get a bunch of numbers, okay? I'm going to write out the numbers as they have on the list. And they even have margins, so 6, 4, 8. 09517 84534 06 489 87201 97245. And we can okay. All right, if you think about it, if I quickly did like a dare on example number 2, the digits are there's only 28 hotels, so I'm only going to use the numbers 0 to 28. Each hotel gets 1, each hotel gets a number. Ignore repeats. Use the random digit table, and after 4 hotels. Right? If you think about it, that's what I'm doing here. And so, okay, so notice that these are double digits for the hotels. So 69 is not a hotel, but 05 is a hotel. So that's hotel number 1. Let me write that. Beach Castle. Okay, let's keep going. Okay, now for this next one, I have 16. It goes across that. And do you have a number for 16? We do, the Radisson. So, Radisson. I'll just put in the number that it refers to, 05. But hopefully you can see in colors that I'm using. Okay. And then 48, no. Okay, 17 on there. Yeah, 17 is on there. 17 is the Ramada. Okay, let's keep going. 87, no, that's not on the list. 17, okay, pay attention. This is a repeat, so we're ignoring repeats. The next number, 40, am I using 40? That number's not on the list. Number 95, no. 17 is a repeat again. 84 is on there. 53. 40, is that on there? No. 64, no. 89, no. 87, and then I have this one right here. I'll use highlighting 20. Okay, so 20 would be the C Club. And if you think about it, I didn't have to use the rest of these digits, which is okay. All right, Go ahead and press pause and use that table now and find me 4 more hotels, but use line 78. And then press play to check your answer. All right, so table D that I gave you guys doesn't have line 78. So go ahead and use line 102. And I also wrote those numbers, and also you can just restart. So let's just pretend you're a different editor for the newspaper, and I send you out, and I want 4 hotels that you're gonna go and interview. Do that brand new, not using the, you can reuse the numbers again. Does that make sense? And then press play when you're ready. All right, so I go through this list. 73 is not on there. 76 is not on there. 64 is too big, so that's not on there. 71 is not on there. 50 is not on there. 99 is not on there. 40. 00, that's not on there. Okay, 19. Let's highlight it. 19 here. Let's try to use a color we have not used. 19. That would be the Sea Castle. Sea Castle. And let's go through 27. That is a number on there. So let's use 27. That's there. Let's write out the name. 27, the Tropical Shores. Okay, 27's repeat. 75, too big. 44, too big. Okay, 26. 26 is on there, so let's go ahead and write that one there. This one's called 26, the Tropical Breeze. That's a 6. Shores was 27. Sea Castle was number 19. Okay, 48 too big. 82 too big. 42 too big. 53 too big. 62 and 90. Okay, if you run in that situation, you can just go to the next line, maybe line 103. So those numbers are 4, 5, 4, 6, 7, 7, 1, 7, 0, 9. So let's go ahead and see. 45 too big. 46 too big. 77, that's a no. 17, I don't think we've used 17 yet, so let's pick a color. Orange, 17. And we did that for the last example, but I'm just telling you guys to start over. So 17 would be the Ramada. Okay, so that's how you would use a random digit table. Let's move on now to page number 3. All right, so learning target number 2, explain the concept of sampling variability and the effect of increasing the sample size. Let me break down those words. Sampling is how do you get them? So go back to Toy Story and the claw. I want to pick a sample. Variability we learned in chapter 1 is spread, or a visual is just like, you go to a big buffet of food, a restaurant, and they're going to have a big spread, a big variability of types of foods. Okay, learning target number 1 here. The fact that different random samples of the same size from the same population produce different estimates is called sampling variability. Variability. And some sample means vary, mean you get different numbers. Even though the samples are selected from the same population, we can reduce sampling variability by using a larger sample size. All right, here's an example, okay? Let's say you guys just wrote an essay for your history or English class, right? And the teacher says, write a 2-page essay on who should be president right now. Should they impeach Trump or not? And they examine the average word length in your essay. Okay, if they randomly pick, remember this is the sample size. If they randomly pick 5 students and they took the average of your word lengths, maybe some of your words, I don't know how many words they picked, but maybe one of the words was 8 words long, and the others, in your essay, I don't know how many they picked, but I'm not going to count up the dots. But what I'm trying to say is that, it looks like, let me highlight this. It looks like in the center here is 5, right? But, maybe you're in AP English, right? Maybe you're more sophisticated. Well, if I increase the sample size, if I get more students now randomly from the school, it looks like it's starting to stack up here in the center. Okay, so even if I increase the amount in my sample, you're seeing that we're trending out the true mean. They call it the true mean, or the true average. Let's try an example. This might make more sense. Example number 3. Do I have to eat my veggies? A recent Gallup poll found that 57.7% of a random sample of 1,947,144 Americans eat produce or vegetables often. For the purposes of this poll, eating produce often is defined as eating the recommended daily allowance of fruits and vegetables at least 4 days in the previous week. Do you think that the percentage of all, okay, this is the population, right? Americans who eat produce who eat produce often is equal to 57.7%. Do you think that happens every time? Like every person I ask in this stats class or in my neighborhood, are they always going to say 57.7%? Like that exact number? The answer is no. Because different random samples will produce different estimated percentages. Right? If you ask my neighbor, maybe he's 25%. Maybe, if I ask someone else in my stats class, that might be 78%. If I asked, a cousin who lives in Asia, what percentage there might be? There might be 33%, right? You're going to get different numbers. So it is unlikely that this particular sample provides a percentage that is exactly correct. That is exactly correct. Right, it didn't actually tell us the, in the sample size, I guess they did, SRS of 1.9 million Americans. If I take another sample of 1.9 million Americans, it might be like 80%. I take another sample of 1.9 million Americans, maybe it is 60%. So there's going to be some variety. The answers or the percentages are going to vary. Okay? If the sample size was decreased, okay, so we're going from a large sample size what is considered large? 10% of the population. Now we're decreasing it to 10,000 Americans, so sounds like a lot, but it's not. What effect would this have on the estimated percentage of Americans who eat produce frequently? Okay, so big idea, if you sample a lot, you're going to get a bigger and better picture of the whole population. But if you have a small sample size, it's just not going to be as accurate. So we would expect our estimate to be further, so not as accurate, from the true percentage of Americans who eat produce regularly. All right, I'm going to go back to my claw idea. And this is every alien in the bowl. Okay, each of those are an alien, okay? Now, if I just pick one of them at random and say, okay, what percent of produce, fruits, and vegetables did you eat this past week? And you give me a percentage, right? Well, if you keep increasing that sample size, let's just say I test 2 of them. Let's say I test 5 of them. Okay, the big idea is, well, if you increase the sample size, well, if I increase it all the way to everyone, I'm going to get the true mean. I'm going to get the true value which the whole population says it. So increasing the sample size is a good idea. Okay? There would be less variability. Okay, let's move on to page number 4 now. All right, page number 4. Learning target number 3. Use simulation. It's kind of like, I don't know what to call it, computer generated, I don't know, this is my definition, computer generating the future, right? They want simulations about how what will happen to COVID. How many people will die in California? How many beds are needed? How many vaccinations will happen by the end of the school year, end of summer, end of 2021? Will Japan able to host the Olympics based on the number of vaccinations to the population and things like that, right? So it's just a prediction. The purpose of a sample is to give us information about a larger population. Right? Let's just say someone or everyone who's being tested today in Orange County for COVID-19, it tells us that's a small sample because that's not everybody, and it tells us the whole picture. Trying to paint us a picture of the whole population. Okay. The process of drawing conclusions about a population on the basis of sample data is called inference. Inference. Because we infer or get tells us information about the population from what we know about the sample. Okay, I have 2, let's use a highlighter here. I have 2 diagrams, so I'm going to color code this so that we don't get lost. Yellow and green, okay? All right, the first one over here is you draw a box and you have all of the population. Whatever you want your population to be. Let's say this is California. And within California is my sample. So what do? We collect data from a representative sample. So that happens first. I get a sample, right? And then, is that purple? And then number 2, we make an inference. Maybe a simple word that you kind of know is a conclusion. An inference or conclusion about the population. So this is kind of going back, right, to explain to us what we know about the population. You know, maybe Rebel TV runs into your classroom second period, and they're like, who got a scholarship? Who got a college scholarship, right? And maybe in that class, like 3 students out of 30 get it. You're like, whoa, 3 out of 30, like, wow, that's amazing. Like, maybe if we don't have time to run to every classroom, but we can say something about the whole school student population. Maybe 3 out of 30 is really good. Like 1 out of 10 or 10% of our students are getting scholarships, right? That's kind of inference or conclusion they would get out of that, okay? All right, here's my second one is, I'm going to call this one notation. Notation. And we'll call this one quantity, or a stats vocab word. We'll call this one statistic. And we'll call this one a parameter. Okay, another word for a statistic is taken from a sample. So hopefully you see the S's there. Statistic is from a sample. A parameter is from the P, population. Like data taken from the population. Okay, so if you have something called the mean, or let's just be super practical, it's the average, right? We would use this notation, X bar. Okay, now if you see the word parameter, it's talking about the whole, the big, all. And you have something there, that one is called mu. Mu, it's a Greek symbol, mu. It's kind of like a U with a longer longer tail. Okay. Standard deviation, that's a measure of variability. You're going to have an S, or in your calculator it would have like SX, sample. This is just from the sample, right? But if it's the whole population, you have this one. I think that one's called sigma. It's an O with a tail on it. I take that back. I don't think it's sigma. Sigma is the E. And we're running out of colors here. Let's see if we can get a dark orange. And the last one is a proportion. And a proportion is a p hat, and there you just have a p. I just wanted to talk about some notation because really the big idea here is a sample versus a population. You get a sample, from the sample is a statistic, S and S. From the population we get parameters, or information from them is called parameters, okay? All right, let's talk about example number 4, Reese's Pieces. Mr. Ng only likes the orange pieces in Reese's Pieces. He looks up the chances of getting a Reese's Pieces on the company's website of getting orange, and it says you have about a 50% chance out of two pieces you will get one orange. That's what they're telling us. Every turn of the candy machine, you get 10 pieces. So you put like a quarter in, you turn the machine, and you get 10 pieces of candy. Well, what's 50% is half, so what's half of 10? So we expect I get 5 orange Reese's Pieces every time we turn it. Out of 10, I expect 5 of them. Well, on the first turn, he only gets 3 orange ones. And the second time, I get 0 orange pieces. 3A, is the machine broken? Or what they put in there, is it rigged? Explain. Make a prediction. What would happen if I turned it 50 times or 100 times? And what would you expect to happen in the long run, 1,000 times? And then we're going to go ahead and click on this app, and we're going to set our adjustments here and then see what happens to our candy machine. Okay? So go ahead and press pause and make a prediction. All right, I'm going to click on this app. And probability, 0.5. Remember, if you 0.50 is equal to 1 over 2, which is 50%. So 50%, I'm going to get orange candies. We said that the number of candies every turn is going to give you 10 candies. And we just want the machine to turn once. Okay? So let's go ahead and turn the machine. Okay, out of 10 pieces of candy, 4 of them were orange, and it placed it here on this dot plot. Do you see that? Remember, I expect half of them, because 50% they say are oranges, right? So that's where it should be. Okay, let's keep sampling. Uh-oh, I got 3, 5, 7, kind of all over the place. This is called variability, sampling variability, because the samples that we're getting are all over the place, right? We got 7 in this last case, but here, this is kind of neat, is I can just now, how many times do I want the machine to basically turn? That's what it's saying. Let's try 10. So now it's going to turn 10 times, and then of the 10 results, it's going to show me 10 more dots of how many were orange, okay? And then after that, it should plot those onto our, so they're saying it turned it, 10 pieces of candy, 6, only 2, and that one's 6, and there it goes, right? I'm going to turn off the animation, and this is say I want 10 more. There it is. They added it there. 10 more. 10 more. Okay, let's just add, let's go crazy. Let's do 100 turns. It's going to add 100 dots. Whoa. Look at that. So many dots, it's going to look like that. Take another 100. Do you see that? Most of the time, we would expect that to get 5 orange pieces of candies. But sometimes it's very, very, very unlikely that all 10 pieces of candy would be orange. This is what happened in our simulation, right? Computer generated for the future, right? No time did I get 0, right? So let's do it one more time. Let's just keep doing this. And if you guys notice the picture, I don't know if you guys notice this. If I draw a curve above it, do you guys know what that looks like? That looks like our bell curve, our normal distribution that we learned previously. So as we take more and more samples, more and more simulations, it is approaching what we would expect. But back in the beginning, only with one sample, with only one turn, it was off, wasn't it? We got 4 pieces of candy when we expected 5. So the simulations can help us, and the more and more samples I take, you can see that most of the time I'm getting 5 pieces of candy. That's what we expect. It's very rare to get something like 9 or 10 oranges, or 0 or 1 oranges, orange pieces of candy. All right, let's go to page 4 and look at example number 5 here. Testing acclaim new or old violins. Old Italian violins, like those made by Antonio Stradivari, are supposed to have the best sound. Stradivari violins are, or they call them Strats, Strat violins are particularly prized and somehow sold for more than $15 million. But could modern or new instruments sound just as good? Researchers designed a study, that's actually a study, you can click on that and read it yourself, in which 10 world-class violin soloists volunteered to play 12 different violins. 6 of these violins were new, and 6 were old. So I'm going to highlight that. So it sounds like we expect, like a 50%, right? Including a Strat. The soloists wore modified welder goggles so that they couldn't visually identify any violins as new or old. After playing these instruments in a practice room, 9 out of 10 violinists identified a new violin as the one that they would choose as a replacement for their current instrument. Determine if these data provide convincing evidence that more than 50% of violin soloists would prefer a new violin to an old one. 100 trials of simulation were conducted. Okay. Each dot in the graph shows the number of violinists out of 10 who preferred a new violin. So, for example, this little dot I'm going to put here, in that simulation, 2 of the 10 preferred a new violin. Assuming each soloist had a 50% chance of choosing a new violin. And I think that's kind of like the other idea right there from that sentence. Okay, explain how the graph illustrates the concept of sampling variability. All right. So remember, variability means the spread. So if the researchers repeatedly take random samples of size 10 from a population of violin soloists, just means they play by themselves with just one instrument, who show no preference for which violin they choose, comma, the number of soloists in a sample who would choose a new violin varies from, so if you let 10 of those soloists try it, and then right here 1 out of the 10 prefer the new one. Or if I do these red dots over here in this simulation right there, just that 1 dot out of 10 soloists, 8 of them prefer the new one. So we can say it varies from 1 to 9. Right? The dots. There's no one who had 0, and there's no one who had 10, which is kind of like off the screen. There, you can see it. Alright. Change colors here. Based on the results of the simulation, is there a convincing evidence that violin soloists would prefer a greater preference for a new violin over an old one? Explain. I think yes. Why? In the study, there were 9 soloists who preferred a new violin. So that is the one singular dot right there. This is, so we're looking at that max there. This is much higher, right? Because we kind of assumed, 6 were new, 6 were old. 9 out of 10 of those violinists, the one in the green box up there, identified the new violin as the one that they would choose as replacement. This is much higher than what we would expect to happen by chance alone. In this simulation, nine soloists preferred 2 R's, I think. Preferred a new violin only one time in 100, which is about 1% of the time in the long run. So even though it's an expensive violin and people are blindfolded, 9 out of 10 violinists wanted the new violin. And if we make the simulation, and so we do it 100 more times, this only happened once. Okay. The violinists were also given a second session in a large concert hall. This time, 6 of the 10 violinists identified a new violin as the one that they would choose. Based on the results of the simulation, is there convincing evidence that the violin soloist would have a greater preference for a new violin over an old one after the second session? Explain. So in this case, I would say no. No. In this study, there were how many? 6 soloists who preferred a new violin after the second session. This is not much higher. Than what we would expect to happen by chance alone. In the simulation, so when we kind of, press play and the computer allows us to kind of see it happen in the future, six or more soloists preferred a new violin how many times? So count all those dots up, that would be 35. 35 times in 100, which is about 35% of the time in the long run. So maybe because they're in the concert hall, they're actually hearing now a better sound, a more true sound of which they would normally play it. And now they're only 6 out of 10 violinists are now preferring this. But if you do the simulation based on, the data given in the original problem, we said, well, only in that green box, only 35 in this case. All right, go ahead and try example number 6. This kind of encompasses everything you've been learning, and then press play when you are ready to go over it. All right, example number 6. Tweet. What proportion? All right, if you look back at our notation above, proportion starts with what? A P, which is talking about a statistic taken from the population. So the whole school is kind of like the population. So we're trying to infer something about the population. To find out, you decide to survey a simple random sample of students from your school. Describe how you would select a simple random sample of 50 students. So I'm going to do a dare. This is the digits. I will use the digits 0, 1 to 50. And how do I assign them? I will number well, take that back. There's more than 50 people in the school, so let's just say there's 2,000. So let's try that again. Doesn't tell you how many, but let's just say 1 to 2,000. I will number each student based on an alphabetical list. And yeah, let's do one with technology so I can show you guys the calculator. Okay, what does R stand for? It is the repeats. I will ignore repeats. And how do we randomize? I will randomize using the calculator. So I want to show you guys that. And how will this end? It will end when 50 students are picked. Okay, what did we say before? So we said using your calculator. Let me show it to you guys. Where's the calculator I like using? Graph and Calc 83. Ooh, look at that. It says fixed dark mode. Super happy. Okay, so I'm going to press, not now, clear. It says math. So far left there next to apps, the blue button. Okay, on the very top, we're going to go to probability, and we're going to look for random integer. Okay, so I'm going to start with 1. Look at the formula, lower, upper, so I want up to 2,000. And then how many do you want it to pick at a time? You could pick 50, but then you might get repeats and have to ignore it. So watch. Let's just say I just do 1. Just want to show you guys this. You can just press enter. That's a random number that calculator's getting me. 7 student 789. 1567, student number 1597, and 1824. So we got lucky and there were no 5. Watch. So second entry, let's say you want to change the formula, and let's just say you wanted to pick 50. It just picked 50 numbers for you. Does that make sense? So that's how you would use a calculator to help generate all the numbers, and then basically you have to pay attention to any repeats. Okay? All right. Will your sample result be exactly the same as the true proportion? What do you guys think? No. Because different random samples will produce different numbers, or in this case, because we're inferring, it says a proportion, different proportions. Right? It could just simply be a yes or no, and then, you survey 50 students and 37 of them say yes, or 16 of them say yes. Every time you take a sample of 50, it's going to be different. That's what we're trying to say. Therefore, it is unlikely that this sample provides a proportion that is exactly correct. Okay, and the last one. Which would be more likely to yield a sample result closer to the true population value? A simple random sample of 50 students or 100? Explain. So which one is bigger? Because of course you want to keep testing as many students as you can. I would love to test all 2,000, but time and money. So I'm going to choose the 100. We would expect our sample proportion, again, that's just saying, have 2,000 students, or out of, say, your simple random sample of 100, 60 of them use Twitter or tweet. So my proportion or fraction is 60 out of 100. But again, if you take more, it's better. We would expect our sample proportion to be closer to the true proportion. I'm going to underline this one. Remember, the true proportion is if you actually tested all 2,000 students at the school. Remember, I assumed that was 2,000. When using an SRS of 100 students rather than 50 students. This is because increasing sample size reduces sampling variability. Remember, if I just test one time, you just get one dot. But eventually, if you keep doing a lot of dots, you'll understand where the true, put that in red there, the true proportion was, right? You don't really know it, but if you keep taking a lot of samples, you'll know it. Here's a real life example, right? As I'm recording this, the Congress is considering should they impeach President Trump. And, you know, they can take surveys of, say, 100,000 people in the United States. That's not totally accurate because, you know, you would want to have a bigger number, like, say, 200,000. Okay, 200,000 is not enough. How about 500,000? How about 1 million? How about 50 million people? How about the whole population of the United States? Is it practical? Can they get it in time? How much would it cost to survey every single human or citizen in the United States? Okay, that's too long. But if you keep taking samples, you'll find out that true mean. All right, so let's review what we've done. Learning target number 1, describe how to obtain a simple random sample using slips of paper technology. That's the DARE. Learning target number 2, explain the concept of sampling variability and the effect of increasing the sample size. You'll eventually go to the true proportion, that middle over there I showed you guys, and using simulation to test a claim about a population proportion. You can use the computer, just like we did with the Reese's Pieces, and get a dot plot, and you'll see that it keeps stacking up to be approximately normal. Taking more samples is good because it goes towards approximately normal. So that's lesson 3.3. Thanks, guys. See ya.
24 hours in a day, and I get to do math, hey hooray. Y equals mx plus b with Mr. Ng, we're making history. Pythagoras, Euclid, and Gauss, learn the math and you'll become the boss.